Um, so let's do you have any questions?
Um, yeah, I was hoping you could maybe go over some of the homework with me and then maybe go over like the railroad process because I'm kind of
Yeah,
struggling with that.
yeah. Let's start with the railroad process.
Oh, okay.
Let's do that. Let me,
It's, just like you go through the whole school system and they teach you in the European or scientific and then when you get to the nuclear industry it's like actually we use the English.
yep, yep. Oh, that worked. Freaking A. All right, so and I'm gonna bring up one of the problems here. It's just gonna take me a second here.
Sure thing. Yeah.
And the problems were 9 through 13,
Um,
um,
well, let me.
something
I
like
think it
that.
was 1 through 9.
Oh, last week's. I'm
Yeah.
just gonna I'm just gonna look at this week's for now. So for this one, I'll work through a current problem because somebody else had asked a question about this week's,
Oh, sure.
and we'll just use that to let's see, we're on page. Holy smokes, are we already on page 50 something? Do I get that right? Pages 35 through 49 is what the reading is. And then the practice problems are 9 through 13.
5 through 49. Yep.
Okay, 20 degrees of subcooling. So this doesn't help with all right, let's go back to last week's.
Sure.
What page was last week's on?
Think that was 32 or 33,
Okay,
1 through 9.
there we go. Yeah, these are good ones for uh, doing the ladder problem. All right, so ladder problems. The way you do these, let's say, all right, let me bring up one more window here. I'm almost there, promise. Everybody that's going to watch this later is like, what's going on? Well, why isn't he
Yeah.
doing anything?
Yeah, I like your setup. Podcast setup.
Yeah, yeah. So do you see this thing that I'm squiggling on?
Yeah, I see that.
Okay. All right, so that's what we're going to use. We're going to look at review problem number one.
Okay.
So it's a 240 pound mass, okay, not pounds force. Operator, he changes elevation by from the 441 foot elevation to 606. So that's a total change of 165 feet. So let's where's my eraser here? Let's start with the equation. What's the equation for what's this asking?
Uh,
Potential energy.
yeah. M times G times Z.
And that's part of the equation.
Hmm.
That is the equation. You just have to know that there's another conversion factor you have to add for your units to work out. So the
Hmm.
actual equation is over G sub C.
Okay. Okay.
So we'll leave that off and we'll do it with the mass times the acceleration due to gravity times the change in height. So what's the mass?
Um. Yeah. However much he weighs, however much
Yeah.
the guy weighs. Yeah.
240 pounds mass.
Yeah.
And we're going to draw a line and we're just going to put a big line all the way across
Okay.
because we're going to have a bunch of things on this ladder. Anything that's on the top of the equation goes above the line. Anything on the bottom of the equation goes below that horizontal line.
Hmm.
So 240 pounds mass. And then the G. What is G? What's the number?
Okay. In English, it's 32.2 feet per second squared.
Yep. 32.2 feet per second squared. And then Z, what's that change in height?
see. Elevate.
165 feet, right? 606
Yeah.
minus 441. All
Yeah. Yeah.
right. So our units here is pounds mass feet squared over seconds squared, which is garbage. That doesn't help us at all
Yeah.
because we need foot pounds of force.
Okay. That's the
So,
unit for potential energy for
yep,
pounds force. Okay.
yep. We use the American units for all this stuff.
Hmm.
All right. So we need to have a conversion factor, and our conversion factor is 30. Oops. It's the same as gravitational acceleration, but it's all it does is it says that every pound mass of accelerated mass is equal to 1 pound force. That's all it says. But you can't just say 1 pound mass equals 1 pound force because your units don't work out. So our units are 32.2 foot pounds mass per pound force seconds squared. This is the conversion factor when you're dealing with converting, when you're converting pounds mass
Okay.
to pounds force.
Mm.
This is what you use. Okay.
Okay. Okay.
Now, you can tell where it goes on the equation because you need the second squared to cancel out. So the second squared cancel out. The pounds mass cancel out. One of the feet cancels out. The 32.2 cancels out. And so what we're left with is 240 times 165
Mm.
foot pounds force.
Okay. Okay.
That's it. And so I've checked my units. I know that I've eliminated everything I need to eliminate, and I've got it down to what is 200 times 165.
So 240 times 165, 39, 600
Yep. Foot pounds force.
pounds force. Okay.
Yeah.
Okay. So the 240 pound mass guy, we take that, convert it to foot pound, I mean to pound force, and we do that by using the 32.2 or pounds
Yeah.
per second squared under, and then underneath that is 32.2 feet pound mass. Okay.
Pounds mass. Yep.
Okay.
And then you just have to have the rest of your data. You have to have your gravitation force, your gravitational acceleration. So you have to have all these pieces for this to work.
Hmm.
You can't just take 240 pounds mass divided by or times the pounds force second squared, 32.2 feet per pounds mass. You also have to have the M and the G and what's the height. So all
Yeah.
three of these things have to be in play for this to work out. But it does end up with the right foot pounds force.
Hmm. Oh, so what's the difference between the top G and then the bottom G sub C? Or
So the top G, let me see if I can find the page. I wrote one of your reading assignments was this thing I'd written up a couple years ago because people had that question, and it's the whole. Um, let's see. I just have to find it. Holy crap! Where did it go? Maybe I didn't do that for you guys. Okay, well, I owe you a lookup. I have a paper that I'd written that I thought I had loaded into here. Let me find pages. View all pages. It's like the final word or gravitational constant in energy problems. Here we go. How do I change what I'm sharing? Easy. There we go. You see the gravitational constant? Oh,
Yeah, yeah.
so let's see. How do I? Is it published? It's published. So this is a good write up. I'll put this in the reading. Um, how do I succinctly say this? So pounds mass is just that. It's just mass.
Mhm.
And if I have 200 pounds mass here on Earth, that's equivalent to 200 pounds force because every pound mass is pounds force. But that's because the force due to gravity is 32.2 feet per second squared. If I take 200 pounds of mass and I take it to the moon, it's going to have less force because the force due to gravity is less. So that 32.2, where it comes from, is based on Earth's gravitational force, the force due to acceleration. Because force is mass times acceleration.
Mhm.
So acceleration is the force of gravity acting on the mass. And since gravitational acceleration is 32.2 feet per second squared, that gives us awkward units of foot pounds mass per second squared. But units of force are pounds force, right? So our conversion, so they came up with the conversion to clean up the units. So all they do is, well, if I take the mass times the height times the gravitational force, the gravitational acceleration, then what units am I left with? What do I need to clean up? Well, they have to have foot pounds mass per pound force second squared. Okay. And that gives us our force over a distance in foot pounds force. So every time we're working with pounds mass in our energy equations, we have to consider the G sub C because,
Mhm.
and that's the difference when you said what's the difference between the first 32.2 and the second 32.2? One of
Yeah.
them is G, one of them is gravitational acceleration. That's the G. The second one is G sub C, and G sub C is a conversion factor.
Mhm.
Okay.
Yeah.
Does that help at all?
So yeah, that's a 240 pound guy, and and we're just we're applying the gravitational constant. That's how much he weighs, his weight on Earth, right?
Yep.
Basically. Okay. Okay.
Yeah.
Okay, that helps.
Okay, good. Let's see. Go back to my tablet. Screen mirroring again.
Okay, I see the iPad now.
Okay. So does that part make sense?
Yeah, yeah.
And then
Maybe you can go over two if you don't mind.
yeah, I'm just trying to remember how to
Oh,
let's see. Oh, there it is. I was looking for how to clear the screen. I couldn't figure it out. All right. Let's see. Do, 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 do. All right. Kinetic energy. All right. So number two is what is the kinetic energy of a 3,000 pound mass car moving at 55 miles an hour? So the equation for kinetic energy equals one half mass velocity squared.
Yeah.
That's what it looks like on the surface. But if you just calculate it like that, you're going to come up with something wrong because we're dealing with mass in pounds mass. So what else do we need?
Yeah, the gravitational constants.
Over G sub C. So we have to divide our mass by our G sub C to get our units to work out. So let's try it out and see what happens.
Okay.
So another way to write that is mv squared over 2 G sub C, right?
Because of the one half. Okay.
Yep. So what's our mass here? 3,000 pounds
Uh,
mass.
yeah.
3,000 pounds mass. I'm going to draw my big line, my little railroad track. So I've got 3,000 pounds mass times velocity squared. So what's the speed of the car?
55 miles per hour.
Okay. So 55 miles in an hour. And we know that we're going to need seconds, right? We're going to need feet per second.
Yeah, yeah.
So 1 mile is equal to 5,280 feet. And 1 hour is equal to what? 3,600 seconds?
Yeah.
So let's try and get some units. The hours cancel out, miles cancel out. So I've got foot pounds mass per second. But I've got and the 55 miles per hour is squared. So there's a better way to do this. Let's convert the 55 miles per hour on its own first. So let me
Hmm.
erase some of this. We'll put the velocity in as feet squared per second squared because we're gonna so 55 miles per hour and 1 mile. I did it again, squared. Actually, we'll come up with our feet per second and then we'll convert it. We'll do the square. All right. Sorry. 1 hour. So 5,280 feet over 3,600 seconds. Okay. So what is this equal? Let's try. We have hour, mile, mile. We're left with feet per second. That's what I want. And 5,280 divided by or times 55 divided by 3,600. It should be get my
I got
calculator
80,
here.
80.66.
80.7, 80.6 something.
Yeah.
Okay, we'll say 80.67
Yeah.
feet per second. So 80.67 is my velocity, but the velocity is squared. So it's 80.67 squared
Hmm.
feet squared over seconds squared. Does that part right there make sense?
Um, oh, why is the bottom second squared?
The whole velocity is squared.
Okay, okay.
You have to square when you square the 80.67 feet per second,
Yeah,
every term in there gets squared. So the 80 gets squared, the feet get squared, and the seconds get squared.
gotcha. Okay.
Okay. And then so now we need our now let's deal with this pounds mass. So we divide 32.2 foot pounds mass per
Hmm.
pound force second squared. Let's do some unit canceling. Second squared cancel out. Our pounds mass cancel out. And one of our feet cancels out. So I'm going to just get rid of that square up there because we still have one of the 2 feet left, right?
Yeah.
So I've got foot pounds force, which is what we want
Yeah.
because that's kinetic energy, potential energy, foot pounds force.
Foot-pounds force.
So
Yeah.
my answer is 3,000
Hmm.
times 80.67 squared divided by 32.2.
6, 7 squared. 2.2. Okay, that's weird. I got like 606,302.69.
Yep.
That's it?
Um, oh, we missed a term. Guess what we missed?
Uh, um,
That is twice what it's supposed to be.
the height?
The two.
Oh, the two. Okay, okay. Yeah.
I was like, so we put the two down
Okay.
there. So
Yeah.
divide that 606,302 foot pounds force by two, and you get 303,151.
Yep. Okay.
And that's the answer.
Okay. Okay. Starting to get the hang of it. Yeah.
Yeah. Um, I'm writing on this tiny little iPad mini, so my screen is a little scrunched for being able to do this, but hopefully you can see it well enough.
Oh, yeah, it's pretty clear.
And the biggest thing is you just get used to whatever your number is, right? And then your units, and then you just draw a line and do your first railroad track. And up here is the top, and down here is the bottom.
Hmm.
So if you were doing something and you had some value in um, feet squared, and you're doing something with pressure, well, 1 foot squared is equal to 144 inches squared, and then you can cancel out your feet squared, and you just know that you have to multiply whatever's on top by 144 to get your inches squared. So the railroad track is all about keeping track of your units.
So do you do a lot of that like on your day-to-day stuff at work or?
No, God,
Oh,
no.
okay.
I don't do math at work.
Yeah.
Just when we're teaching students,
Yeah.
I'm I'm a supervisor of training so that I don't have to do math. All right. Does that help?
Yeah, for sure.
Have you looked at this week's stuff at all yet?
No, I just wanted to make sure I got this last week's down first before I continued on.
Okay, that's fair.
Yeah,
Um,
I'm gonna try not to do everything at the last second though, like last week.
yeah, please.
Yeah.
Yeah. Um,
Um,
mixture of steam and water, enthalpy, degrees of superheat. Yeah, this is all steam table, steam Mollier diagram stuff.
mhm.
So I'm gonna, if you're okay, I'm gonna just walk you through a couple of these, just because
Sure.
another student said she's gonna watch this and wanted some help with it.
Oh yeah, yeah.
Let's look at number 9. I
It's
have the steam tables. Can I pull that up? Let's see. All right.
so 9 of the current week.
Yeah.
Okay.
New share. Let's see. Steam tables. There we go. Yeah. So, number 9 is what is the moisture content, enthalpy, entropy, and specific volume of a steam water mixture at 1,000 psia if its quality is 85%.
Okay.
So let's find, let's see. We need to find what the enthalpy is. 1,000 psia. So this column here on the left in table 1 is temperature. So we're going to
Okay.
go to table 2 because we want that left column to be pressure. So now we're in pressure in table 2. Let's go to 1,000. All right, and we got some numbers here, and I'm going to have to switch my share. So this is the what we're going to be working with is this line right here. Can I highlight that line? There we go. It's this line and these values. And up here is your column, specific volume, enthalpy, and entropy. This first column in each of these is something sub F, and then sub FG and sub G. So the sub F is if this fluid at 1,000 psi was
Mm-hmm.
100% fluid, no gas at all, then this is the value for each of these. This V sub F, H sub F, and S sub F, and that's specific volume, enthalpy, and entropy. So if it was 100% liquid,
Mm-hmm.
which means the temperature's below 544 degrees Fahrenheit at 1,000 psia, then the specific volume would be 0.2, 0.02160. The enthalpy, specific enthalpy, would be 542.6, et cetera, et cetera. Now, if it was 100% steam, which means it had heated it, which means the temperature is greater than 544 degrees Fahrenheit, because anything above 544 degrees Fahrenheit is superheat, which means it's already all turned to steam.
Mm-hmm.
Then you're looking at V sub G, H sub G, and S sub G, entropy sub G, which is gas. The G stands for gas.
Oh,
And what
gotcha.
we're going to be dealing with a lot in this program is we don't care about what it is when it's a liquid. We don't care about what it is when it's steam, especially enthalpy, enthalpy of the liquid and enthalpy of the steam. We care about, the steam is only 98% quality going into the turbine. So there's 2% moisture. What is the enthalpy of that steam? Because it's going to be less than 1192.6 BTUs per pound mass, and it's going to be more than 542.6 BTUs per pound mass. And so that's where the quality and the moisture content comes into place, because we have to figure out it's just basically what percentage of this H sub FG. Now, here's the trick. This middle value is the difference between the liquid and the gas. If I take 1192.6 and I subtract 542.6, I get 650.
Mm-hmm.
This is just the difference between the two. So
And that's a fluid gas mixture, the middle
Yep,
one,
fluid gas
enthalpy.
mixture.
Okay.
So let me go back to, wish I could just really quickly, easily change to my iPad, but doesn't seem to be. All right. So, moisture content.
Hmm.
Um, then we give you quality. Quality equals 85%. Moisture content equals 100 minus quality. So 15% moisture content. Make sense?
15%.
Because it's 100 minus 85.
And that's the moisture content you said?
Yep.
Okay. Okay.
And then what I need to do is I need to find, so I'm going to write these numbers up. H sub F equals 542.6 BTUs per pound
Oh,
mass.
okay. Oh, are you writing on the tablet? Because I'm not seeing anything.
Yeah.
Okay, that's why I was confused. Sorry.
No, it's not letting me. Let's try stop share. Now I lost everything. Where did everything go? Let me get back to my Zoom window. Share iPad. Come on. There we go. This is supposed to be easy. All this technology. All right. Do you see the iPad again?
Now I see it. Yep.
Okay.
Okay, so quality 85%, moisture content.
Oh, it went away again, didn't it?
Um,
Oh, so I can't do this. I'm going to need to bring up the Steam tables on a different screen. It's because I need the numbers from the Steam tables to look. So let me write these down and then I can share my screen. H sub G equals 1192 point 0.6 BTUs per pound mass. And the difference, or H sub FG, is 650.0 BTUs per pound mass. All right, now that I've got those written down, I can go back and resume the screen sharing. There we go. So we know that the quality is 85%. And we
mhm.
know, and we want to know what's the quality of our steam water, or what's the enthalpy of our steam water mixture? Well, if I know enthalpy of our steam water mixture
Mhm.
is equal to our initial enthalpy, the enthalpy of the liquid, plus quality times H sub Fg. So 542.6 plus 80, and I should use my units there, 80.85
Mhm.
times 650. So 85% of that difference between the H sub F and the H sub G. 0.85 times 650 equals, oops, equals 552.5. So this right here is 552.5 BTUs per pound mass. And we're going to add that to 542.6. And that gives us 1095.1. And that's for the H, that's the enthalpy, the specific enthalpy. And we use this equation on the specific enthalpy, the specific entropy, and the specific volume. So you do the same thing instead of H sub F and H sub G and the difference. Well, you don't even need the H sub G. The H sub F and the H sub FG, you do the same thing with V sub F and S sub F. You just do it for all three columns. The exact same thing. Does that make sense?
Yeah. So what's the units for the enthalpy?
BTUs,
Oh,
specific enthalpy, is BTUs per pound mass.
okay. So like how much heat it could hold per
Per pound
pound mass?
mass.
Okay.
Yep.
Okay.
And this is where week 1 or 2 we talked about, or you read about um, the difference between units that are independent of how much mass there is and units that are dependent upon how much mass there is. Because the ones that are independent of how much mass there is are easier to manipulate because you don't care what the mass is. You're
Hmm.
doing it's a specific property based on how much mass you have. So you can do it's some parameter per pound mass.
Hmm.
And then once you have that, then you can say, okay, well, now I have 5 pounds mass of this. Now what's my whole value?
Yeah. Yeah.
Um, Degrees of superheat, the steam at 500 degrees Fahrenheit and 150 psi have. All right, so let's go new share, back to the steam tables. Let's look at number 11. Let's look at the pressure. So 150 psia right here. Oops.
Yeah.
150 psia. The question is asking how many degrees of superheat does steam at 500 degrees have? Well, if it's a steam water mixture, while it's undergoing that phase change, uh, it's in this H sub FG, V sub FG, and S sub FG phase, it stays the same temperature. So anything once it's steam, it has superheat. It's simply 500 minus 358.43. So what's 500 minus 358.43?
500 minus how much? Oh,
See this
358.43.
temperature?
Okay.
Yep.
Yeah. Okay. I got 141.57.
Yep. That's how much superheat it has. That's how much temperature has been added to it after it was fully converted to steam, which is the definition of superheat.
Okay. Okay.
And then,
500.
yep,
So the 500 is the pressure, right? PSIA.
no. If you look
Oh,
at number 11, it says 500 degrees Fahrenheit at
okay.
150 pounds of pressure.
Oh, gotcha. Okay.
And we always care what the pressure is.
Hmm.
Like if you're going to figure out what the properties are, you look at the pressure. So number 12, for example, is at 1,000 pounds. So let's look at 1,000 pounds. And it says that how many degrees of subcooling does water at 420 degrees Fahrenheit have? Well, it's this value minus 420 degrees Fahrenheit.
0.65 minus 420 degrees Fahrenheit. Okay.
Yep. Wait a minute. What minus 160?
Oh, so 544, right? That's
Yeah.
the
Yep.
544.65 minus 420, right?
That's correct.
Okay, 124.65.
Yep. That's it. Super easy.
Okay, okay.
Now, a couple of these others get a little more challenge, not tricky or challenging, but like number 13, it's not asking what is the specific volume and enthalpy of water. It's asking what is the density and enthalpy of the water. Well, density is the inverse of specific volume. So all density is, lock my screen again.
Pounds mass per volume or
Yeah, it's pounds mass per cubic foot. So
Mhm.
you look at the units of specific volume, it's cubic feet per pounds mass. So all you do is one divided by whatever number you come up with for specific volume. So you look at 1000 psia, 400 degrees Fahrenheit, you know it's subcooled, so you know it's completely a liquid. Well, if it's a liquid, then this V sub F is the specific volume for a liquid. And so
Okay.
what's the density? Well, it's 1 divided by 0.02160.
It's the inverse of that
Yep.
value of that volume fluid. Okay.
Yep.
Okay. Okay.
Anybody watching this is going to get a super big help because
Yeah.
I just walked you through most of the practice problems,
Right.
but this is my opportunity to actually teach. So, yeah. All right. But this is all right. Answering a question somebody else had. So, but does that help you? Because I know you hadn't had a chance to look at that yet. Does that make sense?
Oh, that definitely helps. Yeah. Um,
Okay.
and so the entropy, how does that relate to the like I know when I took my physics class, like they were just talking about that was like a measure of randomness in a system, the entropy,
That's
but
that's the chemistry definition of entropy.
mhm,
We're dealing with thermodynamics, and so here's the big complicated answer about entropy. Entropy has a lot of definitions, and nobody's completely decided on what it is.
mhm,
I've got a book on philosophy that lists a bunch of definitions, philosophical definitions. Now, enthalpy has a definition. We've defined it. We know exactly what enthalpy is. All right, it's a pressure times volume plus internal energy of a system. Like it's a thing we can calculate. It's something we can tangibly um, track, measure, and everything.
right.
Entropy's different. Entropy's actually a philosophical concept. We apply units to it, we apply
Yeah.
value to it, but we're just guessing. There's an idea that it's in so it depends on what philosophical content or perspective you come at it with. If you're talking about chemistry, they say, well, it's the measure of disorder in a system,
Mhm,
whatever that means, and it's a stupid definition. And but if you come at it from if you're in thermodynamics, let's say you're studying heat and energy, well, then entropy, the definition of entropy, is different because it has to do with the fact it's part of it's part of the explanation for why things don't get uh, why heat always transfers from hot to cold. Heat always moves in one direction. And the answer to why it always moves in one direction is entropy. And because it's the universe is not a reversible system. And so we don't have a way to, we don't have it's like time flows in one direction. We
mhm,
don't have a way of just, oh, you know what, let me, right, we don't have a way to do that.
Yeah.
um and we don't have a way to reverse the flow of heat processes. We don't have a way to reverse that entropy. So when we talk about reversing entropy in a system, that's a theoretical concept that doesn't match reality. Entropy has a lot of definitions. It's not. It's a page and a half in my book of philosophical definitions,
mhm,
and nobody's decided on it. So it's a lot harder to explain. It's the idea that the universe is that everything is evening out, that heat is transferring from hot to cold, and eventually we're going to lose all our heat sources, and eventually the energy in the universe will will just slowly degrade, and everything's just going to one constant low energy, and then everything ceases to exist.
right. You
That's
can't do any usable work anymore at that point.
yeah, yeah. There's a finite amount of usable of energy in the universe that we can convert to work. And we
Mhm.
can't spontaneously create uh, new out of nothing. It comes from somewhere. It's all the laws of conservation of energy, law of conservation of mass. All these laws of conservation, guess what? It's all entropy. It's all
Yeah.
has to do with the idea that it's not a reversible system. So that was the long, painful answer, um, because it's not an easy. Well, let me explain it to you so you understand it. It's a concept that is still argued about today. Does that I can't. I don't even want to ask if that
What's
helps because I can't imagine
what's
that
the
helps.
usefulness like in terms of like like operating a reactor? Like why do we need what can I
Why, so
yeah
why do we have it in our Mollier diagram? Why do we care about it in our steam tables?
yeah
Because I never got around to answering that. The thermodynamic and definition of enthalpy, right, is the amount of energy in a system available to do work. And what we did is we assigned the opposite of that to entropy, the amount of energy in a system not available to do work. And so
uh,
entropy is the bottom part of that Mollier diagram. And when we're looking at work processes, uh, when we're not doing work, we're moving left to right. The entropy changes. And if we are doing work, entropy doesn't change.
mhm,
So they've not randomly, but they've smartly assigned the definition of entropy as the amount of energy in a system not available to do work when we're talking about thermodynamic systems. When you're talking about chemistry, they use the dumb definition, amount of disorder. When you're talking about heat energy, it's the basis for why things energy flows from hot to cold. Uh, when you're and there's a bunch, there's like a dozen different definitions of entropy. So,
mhm.
but that's
Okay,
why
that helps me
that's
yeah
what
grasp it a
we
little bit better.
okay. That's what we use. That's why we care about it, because we would care about how much energy are we getting, or can we put in our turbine, and how much energy can we get out of this turbine, but how much of this is not available to do work. Did I just do a
I think yeah the oh yeah if you have a Mac then yeah.
see what that does? Anything? Nope. All right. All right. Well, do you need any other questions?
uh None that I could think of, but yeah I think I'll probably be a regular Zoom attender because it's a little challenging subject for me, but yeah I'm definitely gonna work on it.
Okay.
Oh, also, yeah, while I'm here, does it look like any entry level operator positions are opening up soon or anything in operations?
We're not hiring yet.
Okay.
They
Okay.
are talking about when do they want to start a new class, and it looks like maybe June, July of next year of this. So after the outage,
Okay. Okay.
um, one other thing I talked to the operators about is look for anybody that supports the outage, like Day Zimmerman. Day and Zimmerman is a
Hmm.
contract company that supports the outage. Anything you can do to get an outage job,
Hmm.
any outage job, like labor, I'm just going to sweep stuff or move stuff. That's a foot in the door. And
Right.
from there, yeah, the once your foot's in the door, that opens up a lot of things.
Hmm.
So look for contract companies that support the outage. The only one that comes to mind off the top of my head is, there's two: Siemens, Siemens,
Siemens, yeah.
or SEIM, something like that.
Yeah.
And then Day and Zimmerman.
Okay. Okay.
Okay.
Yeah.
So looking for those. Right now, we don't have any job openings for operators, no entry level positions, no non licensed operator positions. Um, Keep an eye open for security jobs. Those are good ones to get. And of course, any HPRP.
Hmm.
Okay.
Hmm. Yeah. Well, I appreciate your time, Jason. Yeah, I'll shoot you the email about the health physics scholarship again. But
Yeah,
yeah,
thank you.
yeah.
All
All
right.
right.
Well, you have a good night.
All right, you too. Bye bye.
Bye.